Hello, friends. Welcome back. Or, if this is your first time finding your way here, welcome. You've arrived somewhere quiet, somewhere soft. Pull the blanket a little closer, let your shoulders drop, and just breathe. Before we begin tonight, if these slow science-filled nights bring you a little peace, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now, let's drift. Close your eyes for just a moment and imagine this. You are standing outside, the air is still, too still. The kind of still that doesn't feel like rest, it feels like waiting. The clouds above you have turned a color that has no good name. Not quite green, not quite gray. Somewhere between the two, and somewhere deep in your chest, before a single raindrop falls, before a single rumble of thunder reaches your ears, you already know. Something is coming. How did you know? Hello, friends. Welcome back, or if this is the first time you've found your way here, welcome. You've arrived on a very good night, because tonight we are going to do something that humans have been trying to do for as long as we have had eyes to look upward. We are going to learn to read the sky. Before we go any further, if you find something gentle and good in these quiet journeys through science, I would love for you to stay. Tap the like button, softly subscribe, if stories told. At this pace feel like home to you, and ring the little bell, not because you have to, but so the next still night, the next wondering can find its way back to you. Now, let's begin. The sky has always been trying to tell us something. This is not a metaphor. This is not poetic exaggeration. It is in the most literal and scientific sense true. The atmosphere above your head right now is a living, breathing, constantly communicating system, and every cloud, every shift in wind, every strange stillness or sudden chill, every color the horizon turns at dusk, all of it is information. All of it is language. And for most of human history, we did not have words for what we were reading, but we read it anyway. We had to. Think about what it meant to be a farmer in ancient Mesopotamia somewhere around 3,000 years before the Common Era. There were no weather apps. There were no satellites. There was no meteorologist on the evening news gesturing toward a green screen with confident hands. There was only the sky, and there was you, and between the two of you, there was an agreement: pay attention, and I will warn you. Ignore me and suffer the consequences. The ancient Babylonians kept some of the earliest written weather records in human history. Clay tablets have been found, actual clay tablets baked hard by the sun thousands of years ago, that contain observations about clouds, about winds, about the behavior of stars in relation to coming rain. They called certain cloud formations by names we can no longer translate exactly. But the intent is clear. They were cataloging. They were noticing patterns. They were in their own ancient and careful way doing science. And here is what makes that remarkable. They were right about many things. Not everything. They also believed that a halo around the moon meant a goddess was angry and that a double rainbow was a divine message about war. But threaded through the mythology, threaded through the omens and the prayers were genuine hard-won observations about how the atmosphere behaves. The ring around the moon, for instance, the ancient Babylonians associated it with coming rain. And they were not wrong. That ring is caused by ice crystals in high cirrus clouds, the kind that often precede a weather system moving in. They did not know why, but they knew that when they saw it, they should probably bring the harvest in. This is one of the most quietly astonishing things about weather science. The data collection started so much earlier than the understanding. Aristotle, writing around 340 BCE, produced a work he called Meteorologica, a word that gives us directly our modern word, meteorology. In it, he tried to explain rain, wind, thunder, lightning, hail, snow, and even earthquakes, all as products of what he called exhalations from the earth. He was wrong in almost every specific mechanism, but he was doing something extraordinary for his time. He was insisting that weather had natural causes, not divine ones, not the breath of gods or the anger of heavens, natural, physical, observable causes. That was a radical thing to say in 340 BCE, and it was the right direction to walk. But here's the thing that I want to sit with for a moment, because I think it is the most important idea we will carry through this entire night together. Most of us, and I say this gently without judgment, because I include myself in this, most of us experience weather as random. We walk outside, and it is raining when we expect it's sun. We check the forecast, and it says 30% chance of showers, and we get a downpour that soaks us completely. We watch the news show a hurricane that somehow strengthened overnight, or a drought that appeared without warning, or a blizzard that arrived 3 days earlier than predicted, and we shrug and say, well, that's weather. Unpredictable, chaotic, random. But here is the truth told quietly on a night like this one. The weather is not random. It has never been random. It only appears random because the system generating it is almost incomprehensibly complex. There is a difference, and this difference matters enormously between something that is truly random and something that follows rules so intricate, so layered, so sensitive to starting conditions that it exceeds our ability to predict. A coin flip is random. There is no underlying logic guiding it, but a hurricane. A hurricane is not random. It is the product of ocean temperatures and atmospheric pressure and wind shear and Coriolis effects and moisture content and 100 other variables all interacting in real time, all following the same physical laws that govern everything else in the universe. It is not random. It is just very, very complicated. And that distinction between random and complex is the one that changed everything about how humans understand the sky. Have you ever stood outside just before a storm and felt that particular electricity in the air? That tightening scientists now know that what you were feeling is partially real, a measurable drop in barometric pressure, a change in humidity, sometimes even a shift in the concentration of negative ions in the air. Your body, millions of years of evolution packed into your nervous system, is genuinely detecting something physical. You are not imagining it. You are reading the weather the way your ancestors read it, through sensation, through instinct, through a wordless knowing that something in the atmosphere has changed. The ancient Greeks had a word, meteora, which referred to things happening in the sky above the earth, things suspended between the ground and the stars. Weather lived in that space, that middle territory, neither earthly nor celestial, but somehow both. And it is fitting, because weather is exactly that. A conversation between the ground and the sky, between the ocean and the air, between the heat of the sun and the cold of the upper atmosphere. It lives in the between. For most of human history, weather was one of the most consequential forces in human life. Empires rose and fell because of it. The Mongol invasions of Japan in 1274 and 1281 were both destroyed not by Japanese military resistance, though there was resistance, but by massive typhoons that the Japanese called kamikaze divine winds that obliterated the Mongol fleets both times. The Norman conquest of England in 1066 was nearly delayed into failure because William the Conqueror waited weeks for favorable winds that refused to come. Napoleon's Russian campaign of 1812 collapsed in large part because of weather, an early and unusually brutal winter that the French armies were not equipped for. General Winter, the Russians called it. And they were not wrong to personify it. It had agency. It had consequences. Weather shaped agriculture, and agriculture shaped civilization. The places where humans first built cities in Mesopotamia, along the Nile, in the Indus Valley, in the Yellow River Basin, were all places where the weather cooperated. Regular rains, predictable floods that deposited fertile silt seasons stable enough to plan around. And when the weather stopped cooperating, when droughts came, when floods came out of season, when the rains failed for years at a time, civilizations did not just suffer. They sometimes simply ended. There is growing evidence that a prolonged drought played a significant role in the collapse of the late Bronze Age civilizations. Around 1200 BCE, a sudden and still somewhat mysterious disappearance of several major cultures across the eastern Mediterranean, all roughly at the same time. The weather did not act alone. but it may have been the weight that broke a structure already under enormous strain. This is worth pausing on, because it means that the question we are exploring tonight, why the weather is not random, what it follows, what rules govern the sky, is not merely a scientific curiosity. It is, in a very real sense, one of the oldest and most urgent questions our species has ever asked. Our ancestors did not study the sky because it was interesting, though it was. They studied it because understanding it was the difference between eating and starving, between surviving a sea voyage and drowning, between a harvest and a famine. And so, for thousands of years, we watched, we recorded, we noticed that certain winds brought rain and other winds brought drought. We noticed that the behavior of certain animals seemed to correlate with coming storms, and some of these observations dismissed for centuries as folk superstition have turned out to have real physical explanations. Cows lying down before rain may actually be responding to changes in humidity that make standing uncomfortable. Swallows flying low before a storm are tracking insects which themselves descend as atmospheric pressure drops. The natural world was reading the weather long before we were, and we learned by watching them. The first genuinely systematic weather observations in the modern sense began in the 17th century, after the invention of the thermometer and the barometer. Evangelista Torricelli, an Italian physicist who was a student of Galileo, invented the mercury barometer in 1643, and with it, suddenly humans had a number, a measurement, a way to quantify something that had previously only been felt. When that column of mercury dropped, rain was coming. When it rose, clearing skies followed. For the first time in history, the sky was not just something you looked at. It was something you could read with instruments. Ferdinand II of Tuscany in 1654 established what is often considered the first organized weather observation network in history, a series of stations across Italy, and as far as Poland, all recording temperature and pressure at set times each day, all sending their data back to Florence. It did not last long, but it pointed towards something. It pointed toward the idea that weather was not local, that what happened in one place was connected to what happened somewhere else, that the sky was a system. That idea that weather is a system, not a collection of isolated events, is the seed of everything that follows. Everything we will explore tonight grows from that single recognition. The sky is not random. It is connected. It is cause and effect stretched across thousands of miles and thousands of feet of altitude, playing out in real time above our heads, following rules we are only now in the last century or so beginning to fully understand. Think about that. We have been watching the weather for thousands of years. We have been writing down what we see for at least 3,000 years. We have had instruments for about 400 years. And it is only within the last century, really, within the last few decades, that we have had the computational power to even begin to model the full complexity of what the atmosphere is doing at any given moment. There is something humbling about that, something that invites, I think, a particular kind of wonder. Not the wonder of already knowing, but the wonder of just beginning to understand something that has been above your head your entire life. And here's the question I want to leave gently hovering as we move forward tonight, like those ice crystals in the high cirrus clouds catching the light, making that halo around the moon that the Babylonians noticed 3,000 years ago. If the weather has always been following rules, always been part of a system, always been the result of causes we can name and measure, why does it still so often surprise us? Why does standing outside before a storm still feel like receiving a message in a language we only half know? Maybe the sky is not speaking too fast. Maybe we are only beginning to learn how to listen. And the first lesson, the one that starts everything, the one without which none of the rest makes sense, begins not here on the ground, but 93 million miles away, where a star is burning and its light is falling on a tilted spinning planet in a way that is anything but equal. 93 million miles away, a star is burning at about 27 million degrees Fahrenheit at its core, and every single second, it releases more energy than all of humanity has consumed in its entire recorded history. That energy travels across the vacuum of space as light, And when it arrives here at this small, tilted, spinning planet, it does not land evenly, not even close. And that simple fact that the sun warms some parts of Earth far more than others is the single most important sentence in all of weather science. Everything else we will explore tonight is a consequence of it. Think about that for a moment. Every storm that has ever formed, every trade wind that ever filled a sail, every monsoon that ever fed a billion people, every blizzard, every drought, every gentle afternoon, breeze that moves through an open window while you are trying to sleep. All of it, every last breath of moving air on this planet, traces back to one thing: the sun does not heat the earth equally. Now most people know in a general way that the equator is hot and the poles are cold. That much is familiar. But what most people do not know, what most people have never been told, is exactly why. And the why, it turns out, is one of the most elegant and surprising ideas in all of Earth science. Hold your hand flat in front of a lamp. The light hits your palm directly, a small, concentrated pool of brightness. Now, tilt your hand at an angle. Watch what happens. The same amount of light now spreads across a much larger area of your hand. It covers more surface, but each part of that surface receives less intensity. The light is the same, your hand is the same. The only thing that changed was the angle. That is exactly what happens on Earth. Because Earth is a sphere, and because it is tilted on its axis at about 23, 5 degrees sunlight arrives at the equator, nearly straight down, concentrated, intense. But the same sunlight arrives at the poles at a steep angle, spreading across a vastly larger surface area, diluted, weakened. A square meter of ground at the equator at noon receives roughly 2.5 times more solar energy than a square meter of ground near the Arctic Circle at the same moment. 2.5 times. Same star, same light, just a different angle. And there is a second factor that makes this even more dramatic, and it is one that almost never gets mentioned in casual conversation: the atmosphere itself. Sunlight traveling straight down to the equator passes through a relatively thin column of air. Sunlight arriving at a low angle near the poles must travel through a much longer path. Through the atmosphere, more air, more particles, more opportunities for that energy to be scattered and absorbed before it ever reaches the ground. The poles are cold not just because the angle is shallower. They are cold because the light arriving there has already been partially drained of its energy just by the journey through more atmosphere. This is worth sitting with. The poles are cold partly because of geometry, partly because of the shape of the planet. And once you understand that, once you feel it not just as a fact, but as an image, the entire engine of global weather begins to make sense in a way it simply could not before. Now here is where the story gets truly interesting. The equator is receiving all of this concentrated solar energy day after day, year after year. The poles are receiving far less. This creates an enormous temperature difference between the equator and the poles, a difference that, depending on the season and location, can exceed 100 degrees Fahrenheit. And the atmosphere, like any physical system, cannot tolerate that kind of imbalance without doing something about it. Nature abhors a gradient the same way it abhors a vacuum. It tries constantly to equalize. And the mechanism it uses to equalize, to move heat from where there is too much to where there is too little, is the thing we call weather. All of it. All of the weather. The entire restless, churning, cloud-building storm, generating, wind-blowing system of the atmosphere is at its deepest level a heat redistribution machine. The atmosphere is trying to balance an energy budget that the sun keeps unbalancing every day continuously for as long as the planet has existed. Weather is not chaos. Weather is the atmosphere doing its job. The ancient Greeks understood something about this in their way. Aristotle wrote about hot air rising and cool air descending, about the way warmth and moisture interacted in the sky. He did not have the physics, but he was pointing at the right process. Hot air is less dense than cold air, it rises. And when warm air rises in one place, cooler air rushes in to fill the space it left behind. That movement of air is wind, and wind at every scale from the breeze through your window to the jet stream 7 miles above your head is ultimately air moving in response to temperature differences. Temperature differences caused at their root by the uneven heating of the sun. Let me give you a picture that I find almost impossibly beautiful in its simplicity. Imagine you are standing on the equator on a clear afternoon. The sun is nearly directly overhead. The ground beneath your feet is absorbing enormous amounts of solar energy, and that energy is heating the air just above the surface. That warm air begins to rise slowly at first, then faster as it continues to be heated, climbing upward into the sky. As it rises, it cools because the atmosphere is thinner and colder at altitude. Eventually, the moisture in that rising air condenses into clouds, enormous towering clouds, the kind that build over tropical oceans every afternoon, like cathedrals of water vapor visible from space. And as that air rises at the equator, it creates a low-pressure zone at the surface, a kind of atmospheric drain, pulling air in from the sides to replace what has gone upward. Meanwhile, up in the upper atmosphere, that risen air can't keep going forever. It spreads out, moving away from the equator toward the poles north in the northern hemisphere, south in the southern, carrying its heat with it. Eventually, it cools enough to sink back down somewhere around 30 degrees latitude north and south. And when it descends, it creates a high-pressure zone at the surface. Clear skies, dry conditions, very little rain. This is not a coincidence. Look at a map of the world's great deserts: the Sahara, the Arabian Desert, the Atacama, the Australian outback, the Mojave, and you will notice something. They cluster with remarkable consistency around 30 degrees latitude north and south. They are there because that is where the descending air arrives, where high pressure reigns, where clouds cannot form. The deserts of the world are a direct consequence of the sun warming the equator. Have you ever wondered why the Sahara is a desert? It is not because of something local. It is because of geometry, because of where it sits on a sphere relative to a star 93 million miles away. This great circulation pattern, warm air rising at the equator, spreading poleward, sinking at 30 degrees, flowing back along the surface toward the equator, was first described systematically by an English amateur meteorologist named George Hadley in 1735. He was trying to explain the trade winds, those remarkably consistent winds that blow from the northeast in the northern hemisphere tropics and from the southeast in the southern hemisphere tropics. Sailors had known about the trade winds for centuries before Hadley. They had relied on them absolutely. They were the engine of the entire age of exploration. Columbus used them. Every European ship crossing the Atlantic used them. But no one had explained where they came from. Hadley did. In the circulation cell, he described that vertical loop of rising and falling air between the equator and 30 degrees latitude is now called the Hadley cell in his honor. It is one of the fundamental structures of Earth's atmosphere. But here is something that Hadley himself got slightly wrong, and it took another century to correct. He described the air flowing along the surface from 30 degrees back toward the equator as moving directly north-south. But real trade winds don't blow straight north-south. They blow at an angle northeast to southwest in the northern hemisphere, southeast to northwest in the southern. Why? Because the Earth is spinning. And here we arrive at one of the most counterintuitive and wonderful ideas in all of atmospheric science, the Coriolis effect. Named for French mathematician Gaspard Gustave de Coriolis, who described it mathematically in 1835, the Coriolis effect is not a force in the traditional sense. It is better understood as an apparent deflection, a curving of the path of moving objects caused by the rotation of the Earth beneath them. In the northern hemisphere, moving air is deflected to the right. In the southern hemisphere, to the left. And this deflection is responsible for something so fundamental to how storms and winds work that without it, our atmosphere would look almost unrecognizable. Here is the common misconception, and I want to address it directly. Because it is one of the most persistent myths in popular science, the Coriolis effect does not determine which direction water drains in your bathtub or sink. That idea is almost everywhere, and it is almost entirely wrong. The Coriolis effect operates at large scales, continental scales. In a bathtub, the shape of the tub, the direction you filled it, tiny irregularities in the drain, all of these easily overwhelm the Coriolis deflection, which at that scale is vanishingly small. The myth persists because it sounds elegant and teachable, but it is not true. The Coriolis effect matters for hurricanes. It matters for the trade winds. It does not matter for your bathtub. What it does do at the scale of hundreds and thousands of miles is organize the atmosphere into rotating systems. High-pressure systems rotate clockwise in the northern hemisphere and counterclockwise in the southern. Low-pressure systems rotate the opposite way. Every spiral you have ever seen in a satellite image of a hurricane or a typhoon, that beautiful, terrible pinwheel shape, is the Coriolis effect at work. The atmosphere spinning because the planet beneath it is spinning, weather as a direct consequence of Earth's rotation. Now, scientists in the 19th century built on Hadley's work to describe the full three-cell model of atmospheric circulation: the Hadley cell in the tropics, the Ferrel cell in the mid-latitudes, and the polar cell near the poles. Each cell is a vertical loop of rising and falling air. Together, they describe the broad skeleton of how heat moves from the equator toward the poles. And between each pair of cells at the surface is a persistent wind belt. The trade winds, the westerlies, the polar easterlies, winds that have blown in the same general direction for millions of years, long before any human being ever set a sail. This is something that stops me every time I think about it. The winds that Columbus felt, pushing his ships westward across the Atlantic in 1492, the trade winds between 10 and 30 degrees north latitude. Those winds were there in exactly the same way when the dinosaurs walked the earth. The details of climate have shifted over geological time, but the basic mechanism, sun heats, equator, air rises, spreads, cools, sinks, flows back, that mechanism is as old as the atmosphere itself. The trade winds that made European exploration of the Americas possible were not created by Columbus or by any human event. They were there blowing steadily for hundreds of millions of years, waiting for someone to use them. And use them, humans did. The age of exploration was not simply a story of human courage and ambition, though it was certainly that. It was also a story of atmospheric physics. The specific routes taken by Spanish galleons, by Portuguese explorers, by Dutch traders, and British naval expeditions, those routes were drawn by the atmosphere. Ships going west from Europe to the Americas traveled south first to catch the trade winds. Ships returning traveled north first to catch the westerlies blowing in the other direction. The map of exploration is a map of circulation cells, Hadley's invisible loops drawn in the paths of ships across the ocean. And here I want to pause and offer a correction to something many of us were taught in school, or perhaps more accurately, something we were not taught at all. The phrase "the weather" implies something local, something that belongs to your town, your region, your country. We talk about our weather as if it begins and ends where we can see. But the uneven heating of the sun creates patterns that operate at genuinely global scales. A heat wave building over the Sahara this week can influence atmospheric pressure patterns over Europe next week. A cold air mass descending from the Arctic over Canada can within days be bringing snow to the Gulf of Mexico. The atmosphere does not respect borders. It does not recognize the edges of countries or continents. It is one fluid, continuous, interconnected system, doing what it has always done, trying to move heat from where there is too much to where there is too little. This is the great lesson of uneven heating. The atmosphere is not happening to you locally. You are experiencing the local expression of a global system. The rain falling on your roof tonight is part of a conversation between the equator and the poles, between a tilted planet and a distant star, between the physics of rising air and the geometry of a spinning sphere. Is it not remarkable that the angle of a beam of light, something as quiet and invisible as the angle at which sunlight falls on a curved surface, can set in motion a chain of consequences that eventually becomes the weather outside your window? The sun does not warm the earth equally. And from that single quiet geometric fact, the entire restless life of the atmosphere flows. The rising air, the falling air, the circulation cells, the trade winds, the westerlies, the deflection of the Coriolis effect, the placement of the world's great deserts, all of it is the atmosphere's answer to one question. How do we balance what the sun made unequal? But warm air rising and cool air sinking, as fundamental as that is only part of the story. Because the atmosphere does not just move horizontally across the surface of the Earth. It also has weight, enormous invisible weight, and that weight is pressing down on everything beneath it right now as you lie there breathing. And whether that pressure is a little higher or a little lower, that seemingly small difference turns out to be the mechanism that decides, with quiet authority, whether today will be sunny or stormy, clear or cloudy, calm or wild. Right now, without feeling it, without seeing it, without any awareness of it whatsoever, you are being pressed down by the weight of an ocean, not water, air, 5 quadrillion tons of it stacked above your head from the ground all the way to the edge of space, pressing down on every square inch of your body with a force of about 14.7 pounds. That is the weight of the atmosphere, and it is not sitting still. It is constantly shifting, rising in some places, sinking in others, pooling and thinning across the surface of the Earth in patterns that have been unfolding since long before the first human being ever looked up and wondered what was happening in the sky. We have been talking about how the sun creates heat differences across the planet and how the atmosphere tries to equalize those differences by moving. But now we need to talk about something more subtle, more invisible, and in many ways more powerful. What happens when that moving air presses down harder in some places than others? What happens when the weight of the sky is not evenly distributed? Because that distribution, that invisible architecture of pressure, is what ultimately decides whether today is sunny and calm or dark and stormy. It is in a very real sense the master switch of all surface weather, and most people have never stopped to think about why. The story of how we came to understand atmospheric pressure is one of the most quietly dramatic stories in the history of science, and it begins not with a meteorologist, not with a weather observer, but with a pump. In the early 1640s, workers in Florence were attempting to build a suction pump to lift water from a deep well. Suction pumps had been used for centuries. The idea was simple enough. You create a vacuum and atmospheric pressure pushes the water up into the empty space. But the Florentine engineers discovered something baffling. No matter how perfect the vacuum they created, the water would not rise more than about 34 feet. 34 feet exactly, and then it stopped. They could not explain it. They brought the problem to Galileo, then near the end of his life, and even he could not fully resolve it. It was Galileo's student Evangelista Torricelli who solved it, and in doing so changed our understanding of the sky forever. In 1643, Torricelli reasoned that if air had weight, real physical weight, then that weight was what was pushing the water up in the first place. The water rose not because of some mysterious sucking force, but because the atmosphere was pressing down on the water in the reservoir, and that pressure was strong enough to push water up a pipe to a height of 34 feet. And no higher, because at 34 feet, the column of water weighed exactly as much as the column of air pushing it from below. Balance. To test this, Torricelli filled a glass tube with mercury, which is about 13.6 times denser than water, and inverted it into a dish. Mercury is so heavy that atmospheric pressure could only push it up about 30 inches before equilibrium was reached. The space above the mercury in the closed tube was a vacuum, the first sustained vacuum ever deliberately created in a laboratory. And the height of that mercury column, Torricelli realized, would change as the atmospheric pressure changed. When he checked it on different days, the mercury rose and fell. The sky, it turned out, did not press down with constant force. It pressed down with variable force. And that variability, that rise and fall of a column of mercury in a glass tube, was the first instrument ever to give humans a window into the invisible architecture of the atmosphere. Torricelli's barometer was one of those inventions that is so simple and so profound that it is difficult to fully appreciate it from the outside. For the first time in history, a number could be attached to something that had previously been entirely beyond measurement: the pressure of the air. And with that number, patterns became visible, patterns that had always been there governing the weather, shaping every clear day and every storm, but that no human instrument had ever been able to detect. Within a decade of Torricelli's invention, the French mathematician Blaise Pascal had used it to demonstrate something extraordinary. He had his brother-in-law carry a barometer up a mountain, the Puy de Dôme, in central France, and record the mercury height at different altitudes. As expected, the mercury fell as they climbed. Higher up, less atmosphere pressing down, thinner air, less pressure. Pascal used this to argue that space itself, the region above the atmosphere, must be a vacuum pressing with zero weight. The atmosphere had a top. It was finite. It was measurable. It was real in a way that, before that mountain climb in 1648, it had never quite been before. Now, let's talk about what pressure actually does to weather, because this is where the physics becomes something you can feel, something you can almost taste in the air. Imagine a column of air over a particular patch of ground. If that air is warm, it is less dense, the molecules are moving faster, pushing each other apart, taking up more space. Warm air is lighter, it tends to rise. And when air rises away from the surface, it leaves behind less air pressing down on that patch of ground. Lower pressure at the surface, a low-pressure system, as meteorologists call it. And something very specific happens in a low-pressure zone. The surrounding air, which is at higher pressure, rushes in to fill the gap. And because of the Coriolis effect, we discuss that rushing air spins. Counterclockwise in the northern hemisphere, the air spiraling inward is then forced upward at the center, and as it rises, it cools and water vapor condenses. Clouds form. Precipitation follows. Low pressure means rising air, which means cooling air, which means clouds and rain and storms. High pressure is the mirror image. When air sinks as it does when it is cool and dense, or when it has been diverged away from the upper atmosphere, it presses down more heavily on the surface. Higher pressure. And sinking air warms as it descends, which means it can hold more moisture, which means clouds cannot form. High pressure means descending air, which means warming air, which means clear skies and sunshine, and in extreme cases, drought. This is the invisible architecture. This is why meteorologists watch pressure maps more carefully than almost anything else. A falling barometer means rising air is coming, and rising air means weather. A rising barometer means sinking air clearing skies and calm. Sailors knew this long before meteorology was a science. They watched the barometer the way a doctor watches a pulse, and they were right to. Here is one of the most common misunderstandings I encounter about weather, and I want to address it directly. Because it matters, many people think that storms form simply because it gets cold. Cold equals storms in the popular imagination. But temperature alone does not make a storm. What makes a storm is the collision, the meeting of air masses with different properties. Different temperatures, different moisture content, different pressures. It is the boundary between air masses, the front, where the atmosphere's most dramatic behavior occurs. The concept of the front, that boundary between warm and cold air, was only formally described and named in the early 20th century, during and just after World War I, by a group of Norwegian meteorologists working at the Bergen School of Meteorology, founded by Wilhelm Bjerknes. Bjerknes was a physicist, not a traditional meteorologist, and he brought to weather science something it had long lacked: mathematical rigor. He and his colleagues, including his son Jacob, who made crucial contributions, developed the first genuinely scientific model of how mid-latitude weather systems form, intensify, and die. They used the word front, deliberately borrowing the military language that was saturating the world in the aftermath of the First World War. Just as opposing armies met and battled along a front line, warm air and cold air met and battled along atmospheric fronts. And like military fronts, atmospheric fronts were where the action was. where the weather happened, where calm gave way to violence and then returned to calm again. The Bergen School model describes something called an extratropical cyclone, the kind of storm system responsible for most of the day-to-day weather in the mid-latitudes, including the United States, Europe, and much of Asia. It begins as a wave, a slight bend in the boundary between a cold air mass and a warm air mass. That wave amplifies. The warm air rises over the cold air undercuts. The warm pressure drops at the center of the developing system. The Coriolis effect sets the whole thing spinning, and within 1 to 3 days, a full-blown storm system has organized itself out of what began as a gentle wobble in a boundary line. The Bergen model, first published in the early 1920s, was so accurate and so elegant that it remains the foundational framework for understanding mid-latitude weather a century later. Now, let me give you a historical example that brings all of this together in a way that is almost too dramatic to believe, except that it is completely true. On September 8, 1900, the deadliest natural disaster in American history struck the city of Galveston, Texas. A hurricane enormous powerful, carrying a storm surge of perhaps 15 feet, came ashore with almost no warning and killed somewhere between 6,000 and 12,000 people. The exact number has never been established. It remains to this day the single deadliest weather event in United States history. What makes the Galveston hurricane so haunting from the perspective of atmospheric science is not just the scale of the destruction. It is the fact that the storm was observable. It was trackable in principle with the instruments that existed at the time. The barometer at the Galveston weather station fell steadily in the days before the storm. A Cuban meteorologist named José Carlos Millas, working with the Baleine Observatory in Havana, had been tracking the storm's path and had warned that it was heading toward Texas. He telegraphed his warnings. They were largely ignored in part because of bureaucratic rivalries between the Cuban Observatory and the United States Weather Bureau, which had a policy at the time of discounting Cuban forecasts. The chief of the Galveston weather station, Isaac Klein, assessed the situation on the morning of September 8th and concluded that the city was not in serious danger. He rode along the beach on horseback, warning residents to move to higher ground, but without the urgency that the situation demanded, because he genuinely did not believe the flooding would be catastrophic. The low pressure at the center of the storm, the falling barometer, the rising winds, all of it was there, in the data, in the instruments, in the physical reality pressing down and spinning above the Gulf of Mexico. But the framework for interpreting that data, for understanding what a falling barometer and a spiraling low-pressure system truly meant for a flat barrier island standing barely 8 feet above sea level, that framework was not yet fully in place. The Galveston disaster became one of the great catalysts for the professionalization and expansion of weather forecasting in the United States. The grief of those thousands of deaths was not wasted entirely. It accelerated the development of better observation networks, better communication systems, and critically, a more rigorous scientific culture around the interpretation of pressure data. It is a terrible kind of lesson, but it was a lesson the atmosphere had been trying to teach for a long time. Have you ever watched a barometer? Have you ever owned one of those old brass instruments that hangs on a wall with a dial that reads stormy on one end and very dry on the other? There is something almost meditative about them. They are measuring at every moment the weight of the entire sky above you, the pressure of 5 quadrillion tons of air reduced to a single number, a single needle on a dial. And that number, that quiet, continuously changing number, contains within it the seeds of whether today will be ordinary or extraordinary, whether the sky above you will open or hold. The relationship between pressure and weather is not perfect. Meteorology is not a simple look-up table, but the basic pattern: low-pressure rising clouds forming storms, developing. High-pressure sinking air warming, skies clearing. That pattern has been confirmed by millions of observations over centuries. It is as reliable as any pattern in atmospheric science. And it is why, when you feel that particular heaviness in the air before a storm, when the pressure drops and the atmosphere seems to be gathering itself, you are not imagining something. You are feeling the weight of the sky change. You are feeling the architecture of the atmosphere shift 1 pascal at a time. Pressure, it turns out, is not just a meteorological measurement, it is something closer to a mood. The mood of the sky. High pressure is the sky at rest heavy and settled, pressing the world gently down into sunshine and stillness. Low pressure is the sky in motion, rising and spinning and building towards something releasing everything it has been holding. And what it holds, what the low pressure systems carry with them, what rises and cools and condenses into clouds and rain and fog and snow, is something that covers nearly 3/4 of this planet's surface and has been shaping weather and climate and life itself for as long as water has existed on Earth. The ocean. Vast, ancient, warm in places and cold in others, breathing moisture into the atmosphere every second of every day, storing heat, releasing it, slowly sending signals into the sky that travel halfway around the world before they arrive at your doorstep as weather. And the ocean's influence on weather goes so much deeper and reaches so much farther in time than almost anyone realizes. In the winter of 1997, something strange began to happen across the entire planet simultaneously. Fishermen off the coast of Peru noticed that the ocean water, normally cold and teeming with anchovies, had turned warm and eerily empty. In Indonesia, rainforests that had not been dry in living memory began to burn. In East Africa, regions that rarely saw rain were suddenly flooded. In California, storms arrived one after another in relentless succession, battering the coast for months. In the American Midwest, the winter was so mild that people walked outside in shirt sleeves in January. In Australia, one of the worst droughts in decades was tightening its grip on the continent. Across 6 continents on every ocean, the weather had gone strange all at once, all connected, all traceable back to a single source. A pool of warm water in the Central Pacific Ocean, an area roughly the size of the continental United States, warmer than normal by just a few degrees. That was all it took, a few degrees of extra warmth in one part of one ocean, and the weather of the entire planet shifted. We have talked about how the sun heats the earth unevenly, about how pressure builds and falls, about how air rises and falls and spins into storms. But all of that, as fundamental as it is, describes only the atmosphere. And the atmosphere, vast as it seems, when you look up at the sky, is only the thinner, faster, lighter half of the Earth's climate system. The other half is something deeper, slower, heavier, and in many ways far more powerful. The ocean covers 71% of this planet's surface. Its average depth is about 12,100 feet. And its capacity to absorb, store, and release heat is so immense that it makes the atmosphere look by comparison almost fragile. The ocean is not a passive backdrop to weather. It is an active, breathing, remembering participant one that operates on timescales. The atmosphere cannot even approach storing heat for decades, circulating water across centuries and sending signals into the sky that reshape weather patterns across thousands of miles with a patience and a reach that no storm system could ever match. And perhaps no phenomenon illustrates this more vividly than the one that caused all of those simultaneous disruptions in 1997 and 1998, the climate pattern known as El Niño. The name El Niño, which means the little boy or the Christ child in Spanish, was given to it by Peruvian fishermen who noticed that every few years around Christmas time, the normally cold waters off their coast would turn warm. The fishing would fail. The rains would come. And then after months, things would slowly return to normal. They named it for the season of its arrival. They had no idea in those early observations that what they were watching was the surface expression of a planetary scale conversation between the ocean and the atmosphere. A conversation that had been happening for thousands of years, reshaping weather patterns across the entire globe every time it shifted. Here is what actually happens during El Niño, told as plainly and carefully as I can. Under normal conditions, the trade winds blow steadily westward across the tropical Pacific Ocean, from South America toward Australia and Indonesia. These winds push warm surface water westward, piling it up in the western Pacific. The seas around Indonesia and the Philippines are normally several inches higher and several degrees warmer than the seas off Peru. As the warm water moves west, cold water from the deep ocean wells up off the coast of South America to replace it, a process called upwelling. This cold water is extraordinarily rich in nutrients, which is why the fisheries off Peru are among the most productive in the world. The whole system, trade winds blowing west, warm water piling up in the west, cold water upwelling in the east, is a stable self-reinforcing cycle that drives weather patterns across the entire Pacific and beyond. But every 2 to 7 years, for reasons that scientists still do not fully understand, this system weakens. The trade winds slacken. The warm water that has been piling up in the western Pacific begins to slosh back eastward like water in a tilted bowl returning to level. The cold upwelling off South America slows or stops. Sea surface temperatures in the central and eastern Pacific rise sometimes by as much as 3 to 5 degrees Celsius above normal, and the atmosphere, which is exquisitely sensitive to the temperature of the ocean surface beneath it, responds. The patterns of convection of rising moist air, of cloud formation and rainfall shift eastward. Weather systems that normally form over Indonesia form instead over the open Pacific. The entire planetary weather machine, which has been tuned to one configuration, is abruptly retuned to another. The consequences ripple outward in every direction. Australia and Southeast Asia, which normally receive abundant rainfall from the warm western Pacific, go into drought. The eastern Pacific, normally dry, becomes stormy. The jet streams, those high-altitude rivers of fast-moving air that steer storm systems across the mid-latitudes, shift their tracks. Different parts of North America receive more or less winter rainfall and snowfall. The Atlantic hurricane season tends to be suppressed because El Niño increases wind shear over the Atlantic, which disrupts developing storms. The Indian monsoon can weaken or shift. Coral reefs bleach from the warmth. Fisheries collapse, wildfires ignite, floods overwhelm infrastructure built for a different rainfall pattern. And all of this, every displaced storm, every failed harvest, every flooded valley and parched riverbed traces back to the pool of warm water in the Pacific. A few degrees of extra heat in a body of water that most people on Earth will never see. The 1997 to 1998 El Niño was one of the strongest ever recorded. It was associated with roughly 23,000 deaths worldwide and caused economic damages estimated at over $35 billion. But here is what is important to understand. El Niño did not create bad weather. It displaced it. It rearranged the patterns. It moved rainfall from places that expected it to places that did not. It warmed winters that should have been cold and cooled regions that should have been warm. The total amount of energy in the system did not suddenly increase. The geometry of the rearrangement was what made it so destructive because human civilization, our cities, our farms, our water systems, our flood defenses are all built around assumptions about where the weather normally goes. When those patterns shift even temporarily, the infrastructure of daily life is revealed as surprisingly fragile. El Niño has a counterpart, a cooler phase of the same oscillation called La Niña, which means the little girl. During La Niña, the trade winds strengthen rather than weaken. The cold upwelling off South America intensifies. Sea surface temperatures in the central Pacific drop below normal. And the weather consequences are in many ways the mirror image of El Niño. Australia tends toward flood rather than drought. The Atlantic hurricane season becomes more active. The American Southwest tends toward drought. The Pacific Northwest tends toward wetter conditions. The pattern swings from one extreme to the other and then back again in a cycle that researchers now call the El Niño Southern Oscillation, or ENSO. one of the most powerful drivers of year-to-year weather variability on the planet. ENSO was not scientifically understood until the late 20th century, despite the fact that it had been quietly shaping civilizations for millennia. There is growing evidence that severe ENSO events contributed to food shortages and social instability in civilizations as far back as ancient Egypt, where the flooding of the Nile, so central to agricultural life, was indirectly modulated by ENSO-driven changes in tropical rainfall patterns. A strong El Niño could weaken the Ethiopian highlands monsoon, which fed the Nile, leading to reduced flooding, failed crops, and famine in the Nile Valley. Ancient Egyptians blamed their gods. They were actually responding to a pool of warm water in the Pacific Ocean, thousands of miles away, that no Egyptian had ever seen or could have imagined. This is one of the things I find most quietly astonishing about climate science. The connections between cause and effect are so long, so indirect, so separated in space and time that for most of human history they were completely invisible. The fishermen of Peru saw the warm water and the empty nets. The farmers of Egypt saw the low Nile and the failing grain. Neither group could have known that they were both reading the same signal. It took satellite technology, global ocean temperature monitoring, and decades of careful data analysis before scientists could draw the lines connecting those distant dots. Now, let me introduce you to something even slower than ENSO, something that operates not on a cycle of 2 to 7 years, but on a cycle of centuries to millennia, something that transports not just heat, but enormous volumes of water across the entire global ocean in a continuous, slow, majestic circulation. It is called the thermohaline circulation, and it is sometimes referred to, with both accuracy and a certain poetry, as the global ocean conveyor belt. The word thermohaline comes from two Greek roots, thermo, meaning heat, and haline, meaning salt. The thermohaline circulation is driven by differences in both temperature and salinity, the two properties that determine the density of seawater. Cold water is denser than warm water. Salty water is denser than fresh water. And where seawater becomes very cold and very salty, as it does in the North Atlantic, where surface water cools in winter and becomes saltier as sea ice forms, leaving its salt behind, it becomes dense enough to sink. It sinks to the deep ocean floor and begins a journey that will take it at the pace of a slow drift through the deep Atlantic, around the tip of Africa, into the Indian Ocean, into the Pacific, and eventually back again, a journey measured not in days or years, but in approximately 1,000 years. This deep circulation connects every ocean on the planet. It carries cold, dense, oxygen-rich water into the deep ocean, and brings warmer, nutrient-rich water to the surface in different parts of the world. And the surface branch of this circulation, the warm current that flows northward along the surface of the Atlantic, is something you may know by another name, the Gulf Stream. The Gulf Stream carries an almost incomprehensible volume of warm tropical water northward along the eastern coast of North America, and then across the Atlantic toward Europe. It transports roughly 30 million cubic meters of water per second. That is about 150 times the combined flow of all the rivers on Earth. And the heat it delivers to the North Atlantic has a direct and measurable effect on the climate of Western Europe, Britain, Ireland, Norway, the Netherlands. These places are at roughly the same latitudes as parts of Canada and Alaska. They should, by latitude alone, have winters that resemble Labrador or Anchorage. They do not. They have relatively mild, wet winters. The reason is largely the Gulf Stream delivering heat from the tropics to the northeast Atlantic, warming the air above the ocean, and that warmed air blowing onshore across Europe. Benjamin Franklin in 1786 produced the first reasonably accurate chart of the Gulf Stream, based largely on information gathered from Nantucket whalers who had been navigating it for generations and knew its warmth and its currents by direct experience. Franklin noticed that ships carrying mail from England to America were taking weeks longer than ships going the other direction, even though they were covering the same route. He interviewed the Nantucket sailors, and realized that westbound ships were unknowingly fighting against the Gulf Stream, a river of warm water flowing northeast in the middle of the Atlantic, rather than going around it. His chart of the Gulf Stream, rough as it was, is one of the founding documents of oceanography. Here is the question I want to leave gently hovering in the air for a moment, because it matters enormously, and we are only beginning to understand the answer. What happens to the thermohaline circulation to the Gulf Stream, to all of it as the planet warms? As global temperatures rise, two things happen to the North Atlantic that are relevant here. First, the water becomes warmer, which makes it less dense and less inclined to sink. Second, Greenland's ice sheet melts, pouring enormous quantities of fresh water into the North Atlantic. And fresh water is less dense than salt water, which also reduces the sinking. Both effects work in the same direction. They slow the thermohaline circulation. They weaken the conveyor belt. And a weakened conveyor belt means less warm water delivered to the North Atlantic, which means potentially colder winters in Europe, even as the rest of the planet warms. The ocean, which has been moderating European climate for millennia, may, if disturbed enough, do the opposite, delivering not warmth, but cold to the very places that have come to depend on its warmth. Research published in recent years suggests that the Atlantic thermohaline circulation is already at its weakest point in at least a millennium. The evidence comes from ocean temperature patterns, from sediment cores, from careful analysis of the fingerprints that a slowing circulation leaves in the temperature record of the North Atlantic. The full implications are still being studied. The exact trajectory is uncertain, but the direction of the signal is clear, and it is a reminder of something fundamental: the ocean is not a passive reservoir. It is a dynamic, responsive, memory-laden system, and what we do to the atmosphere, the ocean records, and what the ocean records, it eventually sends back. The ocean remembers everything. It remembers the warmth of last century's industrial emissions stored in its depths against the day it releases them. It remembers the freshwater pulse of glaciers that melted 12,000 years ago, written in the salinity gradients of its deep water. It remembers every El Niño, every La Niña, every shift in the trade, wins every degree of warming at the surface, and it breathes all of it slowly and inexorably back into the sky. And the sky, in turn, expresses what the ocean whispers to it in rainfall and drought and storm tracks shifted and seasons lengthened in weather that arrives not randomly, but according to a logic written in water and salt and the slow memory of the deep. But there is another place where weather is written, before it reaches you, a place so close that you can see it every time you look up, so familiar that it has almost become invisible. Something that drifts across every sky, in every country, in every season, silent and enormous, and constantly making decisions about what kind of weather you are about to experience. You have been watching them your entire life without knowing quite what they were telling you. And it turns out they have been telling you everything. Look up at the sky right now, or imagine it if the ceiling is all you can see. Somewhere above you at this very moment, there are clouds. Maybe a thin veil of white so high and so faint, you almost mistake it for the blue of the sky itself. Maybe great rounded towers of white building, slowly upward like cathedrals in slow motion. Maybe a flat gray ceiling, pressing down on the world uniform, and quiet, holding its moisture like a held breath. You have seen all of these. You have looked up at them your entire life. And most of us, if we are being honest, have thought of them as background, as scenery, as the sky's decoration. But clouds are not decoration. They are not passive. They are not simply water vapor that happens to be visible. Every cloud in the sky right now is a decision in progress, a record of atmospheric processes that have already happened, and a forecast of atmospheric processes that are about to happen. Clouds are the atmosphere's most legible handwriting, and once you learn to read them, the sky is never quite the same again. The story of how humans learned to read the handwriting is one of the most unexpectedly moving stories in the history of science. And it begins not in a laboratory, not in a university, but in the private notebooks of a young London pharmacist who spent his evenings watching the sky. His name was Luke Howard. He was born in 1772, the son of a Quaker businessman trained as a chemist and employed for most of his adult life in the perfectly ordinary business of making and selling medicines. But from his early 20s, Luke Howard was obsessed with the sky. He kept meticulous weather records. He observed clouds with the kind of patient, systematic attention that most people reserve for pursuits far more obviously rewarding. And in 1802, at a meeting of a small amateur scientific society called the Ascesian Society in London, he delivered a paper that would change meteorology forever. The paper was called On the Modifications of Clouds. And what Howard did in it, what seems simple now but was genuinely revolutionary at the time, was give clouds names, not poetic names, not the names of gods or seasons or moods. Scientific names in Latin organized by form and by the altitude at which they formed. He proposed three fundamental cloud types: cumulus from the Latin for heap or pile, stratus from the Latin for layer or spread out, and cirrus from the Latin for curl or fiber, like a lock of hair. And he proposed a fourth type, nimbus from the Latin for rain cloud, to describe any cloud actively producing precipitation. Every combination and variation of cloud in the sky, Howard argued, could be described using these building blocks and their combinations. The response was extraordinary. Howard's classification was adopted almost immediately across Europe. Goethe, the great German poet, who was also a serious amateur naturalist, read Howard's paper and was so moved that he wrote a series of poems in Howard's honor, one for each cloud type. He called Howard the man who named the clouds. The German naturalist Alexander von Humboldt praised the system. Within a decade, Howard's Latin cloud names had spread across the scientific world and were being used by meteorologists from London to St. Petersburg. They are still the names we use today. When a weather forecaster talks about cumulonimbus clouds producing severe thunderstorms, they are using the vocabulary that a London pharmacist invented on his evenings off more than 200 years ago. But Howard did more than name clouds. He understood something about them that had not been clearly articulated before, that cloud type and cloud altitude are not random, that specific types of clouds form at specific heights in the atmosphere for specific physical reasons, and that the sequence in which different cloud types appear, the order in which they arrive as weather systems approach, tells a story. A legible story, if you know how to read it. Let me walk you through that story because it is one of the most beautiful things in all of atmospheric science. Imagine a weather system, a mid-latitude cyclone of exactly the kind we described in the last section, approaching from the west. It is still perhaps 1,000 miles away. The center of the low pressure with its rising air and thickening clouds has not yet arrived. But at altitude at 20,000 feet or more, in the upper troposphere, thin, wispy cirrus clouds have begun to appear. They are made not of liquid water droplets, but of ice crystals impossibly fine, strung out in long streaks across the blue sky. They are beautiful, and they are a warning. Cirrus clouds at high altitude spreading and thickening over the course of several hours are often the first visible signal that a warm front is approaching. The atmosphere is already changing at altitude. The surface has not yet felt it, but the sky is writing the message if you know how to read the handwriting. Over the next 12 to 24 hours, as the weather system draws closer, the cirrus thickens into a higher, more continuous layer called cirrostratus. This is the cloud layer that creates the halo around the sun or moon, that ring of light that the ancient Babylonians noticed and associated with coming rain. They were right. The halo is caused by sunlight refracting through the hexagonal ice crystals of the cirrostratus layer. It is a genuinely reliable indicator that a weather system is approaching. Folk wisdom and atmospheric physics in perfect agreement. The cirrostratus thickens and descends, becoming altostratus, a mid-level layer of gray or blue-gray cloud that dims the sun to a pale disk, like light through frosted glass. Then lower still, as the front arrives, comes the nimbostratus, the classic rain cloud, a thick, dark, featureless gray layer that covers the entire sky and produces steady, prolonged rain or snow. This is not a brief shower. Nimbostratus means hours of precipitation. The whole sequence cirrus to cirrostratus to altostratus to nimbostratus is the atmosphere writing the arrival of a warm front in the sky, one layer at a time, over the course of a day or two. Now here is a question worth sitting with. How many times have you seen that sequence without knowing what it meant? How many times have you looked up, noticed the sky getting milky and then grayer and then darker, and simply waited for the rain, without realizing that the sky had been announcing it in its quiet and methodical way for the better part of a day? The other great cloud drama of the atmosphere is almost the opposite in character, where the warm front sequence is slow and layered and gradual, a long announcement. The cold front sequence is sudden, violent and vertical. Cold fronts move faster than warm fronts. The cold air undercuts the warm air sharply, forcing it upward rapidly, rather than allowing it to glide gradually over the top. And rapid upward forcing of warm, moist air produces the most dramatic clouds in the atmosphere, cumulonimbus. A mature cumulonimbus cloud is, in purely physical terms, one of the most powerful structures that naturally occurs on this planet's surface. It can extend from a base at perhaps 2,000 feet above the ground all the way to the tropopause, the boundary between the troposphere and the stratosphere, at roughly 40,000 to 50,000 feet. That is higher than commercial aircraft cruise. Its top flattened by the stable air of the stratosphere into the characteristic anvil shape, can spread across hundreds of square miles. Inside, updrafts can exceed 100 miles per hour. A large cumulonimbus contains at any given moment somewhere between 300,000 and 400,000 tons of water in liquid and ice form. The electrical charge separation within it, positive charge building at the top, negative at the bottom, can generate voltage differences of hundreds of millions of volts, releasing them in lightning bolts that heat the surrounding air to 5 times the surface temperature of the sun. And that energy, that almost incomprehensible energy, packed into a column of cloud, was released by something as simple as warm, moist air being pushed upward faster than it could spread out. The atmosphere took moisture and instability and converted them through the simple physics of rising and cooling and condensing into one of the most dramatic electrical phenomena on Earth. Benjamin Franklin understood something about this in 1752, when he flew his kite in a thunderstorm, or more accurately, when he flew his kite near a thunderstorm, since direct lightning strike would almost certainly have killed him. What Franklin was testing was his hypothesis that lightning was electrical in nature, that the storm cloud was essentially a giant capacitor building up electrical charge. He was right. And his invention of the lightning rod, a grounded metal conductor that provides a safe path for lightning to discharge into the earth, was one of the first practical applications of meteorological science. One of the first times that understanding a cloud led directly to protecting human life from its consequences. Now, let me address a very common misunderstanding about clouds that I think is worth correcting here, because it comes up constantly and it matters for how we think about the atmosphere. Many people believe that clouds trap heat, that they act like a blanket over the earth warming the surface. And this is partly true, but only partly, and the full picture is considerably more interesting. Clouds actually have 2 competing effects on temperature, and which effect dominates depends on the type of cloud. Low, thick clouds like stratus and stratocumulus are very good at reflecting incoming sunlight back into space before it ever reaches the surface. This is the albedo effect. A thick cloud deck over the ocean can reflect 60 to 90% of incoming solar radiation. These clouds cool the surface. They are essentially a sunshade. On an overcast summer day, the reason it is cooler than a sunny day is largely because low clouds are bouncing the sun's energy back into space. High, thin clouds like cirrus do the opposite. They are too thin and too cold to reflect much sunlight. But they are effective at absorbing and re-emitting the infrared radiation that the Earth's surface emits, upward trapping heat that would otherwise escape to space. Cirrus clouds warm the surface slightly. They act more like a greenhouse than a sunshade. The net effect of clouds on the Earth's energy balance is one of the most complex and actively debated areas in climate science. Whether more cloudiness overall warms or cools, the planet depends critically on what kinds of clouds form, at what altitude, at what latitude, at what time of day, and how those characteristics change as the climate warms. This cloud feedback problem, the question of how clouds will respond to a warming planet and whether that response will amplify or dampen the warming, is one of the largest sources of uncertainty in climate projections. Scientists suggest that understanding cloud feedbacks better may be the single most important step toward narrowing the range of possible climate futures. Think about that. The most sophisticated computer models in the world, running on the fastest supercomputers ever built, still struggle to fully represent what clouds do. These things you look at casually every morning, out your window, these masses of water vapor and ice that have been forming and dissolving in the sky since before there were eyes to see them, remain in important ways at the frontier of human knowledge. There is something I find deeply quieting about that. The sky is not a solved problem. The clouds are not fully understood. After all the centuries of observation, after Luke Howard's careful Latin names, after satellites and radar and supercomputers, the cloud outside your window still contains questions that have not been answered. And there is one more thing about clouds that I want to leave with you, because it is the kind of fact that changes how you look at the sky. Every cloud you have ever seen, every single one, from the smallest wisp of cirrus to the largest cumulonimbus towering above a summer thunderstorm, formed around something. Not nothing, not pure vapor condensing on itself. Water vapor does not spontaneously become a droplet in clean air. It needs a surface to condense on, a nucleus. And in the atmosphere, those nuclei are everywhere. Dust particles, sea salt, crystals carried aloft by breaking waves, smoke particles from wildfires, pollen from flowers and trees, even bacteria, living microscopic organisms that float in the atmosphere, and some research suggests may actually influence cloud formation and precipitation. The clouds above you right now may contain particles of Saharan dust that cross the Atlantic, sea salt from a wave that broke on a Pacific beach last week, smoke from a fire burning in a forest on another continent, pollen from flowers you have never seen in places you have never been. Every cloud is in a sense a meeting place, a gathering of particles from all over the world, brought together by the winds we have been talking about, condensed by the pressure changes and temperature differences we have explored into this temporary, luminous, endlessly changing structure hanging above your head. Clouds are not background. They are not decoration. They are the atmosphere's most visible, most readable, most beautiful expression of everything it is doing and has been doing for billions of years. They are the sky writing its story in water. And once you learn to read them, you cannot quite look at them the same way again. Now, clouds form and move and carry their moisture wherever the winds take them. And those winds, the great persistent winds of the planet, the ones that have been blowing in the same direction for millions of years, longer than our species has existed. Those winds follow paths that are as fixed and as mappable as rivers. Invisible rivers of air, some of them miles wide and miles deep, flowing at hundreds of miles per hour, high above the surface, shaping weather and climate across continents, steering storms and calming seas, and quietly, inexorably determining where on this earth the rain will fall. In the summer of 1944, Allied military planners were preparing for one of the most consequential bombing campaigns in the history of warfare, the Strategic Air Campaign over Japan. B-29, superfortress bombers flying from bases in the Mariana Islands, would need to cross thousands of miles of open Pacific at high altitude to reach their targets. The mission planners had done their calculations carefully. They knew the fuel loads, the bomb weights, the cruising speeds. What they did not fully account for, what almost no one in the Western military establishment fully understood at that moment, was that at 30,000 feet above the Pacific Ocean, there was a river. Not a river of water, a river of air, moving west to east at speeds that sometimes exceeded 200 miles per hour. A current of wind so powerful and so persistent that it could add hours to a flight going one direction and shave hours off. A flight going the other. The first B-29 crews who encountered it were baffled. Flying into it, their ground speed dropped so dramatically that some aircraft barely made forward progress, despite their engines running at full power. Flying with it, they were hurled across the sky faster than their instruments suggested was possible. They had discovered the jet stream, and in doing so, they had stumbled into one of the most important and least discussed features of the entire global atmosphere, a feature that has been shaping the weather of the mid-latitudes for as long as the Earth has had an atmosphere in roughly its current form. And that determines day by day and season by season where storms go, where they intensify, where they die, and what kind of weather falls on the cities and farms and lives of hundreds of millions of people below. Wind, as we have explored, is air in motion. It moves because of temperature and pressure differences. It curves because of the Coriolis effect. It organizes into belts trade winds, westerlies, polar easterlies that have been blowing in the same broad directions for millions of years. But the jet streams are something more than a wind belt. They are the atmosphere's fast lanes, concentrated corridors of extraordinarily fast-moving air at the boundary between the troposphere and the stratosphere, driven by the sharp temperature contrast between the cold polar air and the warm tropical air beneath them. And what they do to weather, how they steer systems, how they amplify or suppress storms, how their shifting position redistributes rainfall and drought across continents, is something that atmospheric scientists are still working to fully understand. Let me explain how jet streams form, because the mechanism is genuinely beautiful in its logic. We established that the atmosphere moves heat from the warm equator toward the cold poles. And we established that the Coriolis effect deflects moving air to the right in the northern hemisphere. Now, imagine air at high altitude moving poleward from the tropics, carrying heat rising, spreading. As it moves poleward, the Coriolis effect deflects it to the right, which in the northern hemisphere means deflecting it eastward. The farther poleward it moves, the more it is deflected. Eventually, instead of continuing toward the pole, the air is moving almost entirely west to east. And because the temperature contrast between the tropics and the poles is sharpest in the mid-latitudes, the air moving along that temperature boundary accelerates dramatically. The greater the temperature contrast, the faster the jet stream. In winter, when polar temperatures plunge and the contrast sharpens, jet streams intensify. In summer, when the poles are relatively warmer, and the contrast weakens, jet streams slow and shift poleward. The primary jet streams in each hemisphere, the polar jet streams, sit at roughly 30,000 to 40,000 feet, meandering between about 30 and 70 degrees latitude, blowing generally from west to east, but rarely in a straight line. They loop and curve in great sweeping waves called Rossby waves, planetary scale undulations in the flow of the jet that carry cold air southward on one side and warm air northward on the other. These waves are not random. They are driven by the geography of the Earth beneath them, by the position of mountain ranges, by the temperature contrast between continents and oceans, by the distribution of snow and ice. The Rockies and the Himalayas, the two great mountain barriers of the northern hemisphere, both perturb the jet stream, forcing it into specific patterns that have remained roughly consistent for as long as those mountains have existed. And here is where weather becomes genuinely personal. The position of the jet stream on any given day determines almost everything about the weather you experience if you live in the mid-latitudes. When the jet stream passes to your north, you are in the warm air to its south, mild temperatures, perhaps some moisture from the south, but generally settled conditions. When the jet stream passes directly overhead or dips southward to pass to your south, you are on the cold side, and more importantly, you are in the zone of maximum atmospheric disturbance where the temperature contrasts. The jet is riding are most intense and where storm systems are most likely to form, intensify, and move. The jet stream, in a very real sense, is the highway along which weather systems travel, low-pressure systems. The storms we discussed in connection with atmospheric pressure form preferentially along the jet stream, spin up as they track eastward beneath. It draw their energy from the temperature contrast that the jet is exploiting and decay when they move off the jet, or when the temperature contrast weakens behind them. Understanding where the jet stream is on a given day is one of the single most important pieces of information a meteorologist can have. Now let me tell you about something that happened in the summer of 2003 that illustrates with terrible clarity what the jet stream can do when it behaves in an unusual way. In the summer of 2003, the jet stream over Europe shifted. Instead of tracking across the British Isles and into Scandinavia, as it normally does in summer, it looped far to the north, leaving Western and Central Europe sitting in a persistent region of high pressure, a heat dome with no jet stream overhead to bring Atlantic weather systems and cloud cover. The result was a heat wave of a severity that Western Europe had not experienced in recorded history. For 2 weeks in August, temperatures across France, Germany, Spain, Portugal, Italy, and Switzerland exceeded 40 degrees Celsius, 104 degrees Fahrenheit, on multiple consecutive days. In Paris, the temperature reached 40 degrees Celsius for the first time since records began. In the United Kingdom, temperature records that had stood since the 19th century were shattered. In Switzerland, glaciers lost more mass in those 2 weeks than in any comparable period in living memory. The human cost was staggering. Estimates of excess mortality across Europe during the 2003 heat wave range from 35,000 to 70,000 people, most of them elderly, most of them in urban areas where the heat island effect compounded the already extreme temperatures, most of them in countries where air conditioning was rare, because summer heat of that severity had simply never been considered a serious possibility. France alone lost an estimated 15,000 people in the space of 2 weeks. The French government caught almost entirely unprepared, with many officials and medical personnel on their August vacations, was deeply shaken. It triggered a fundamental rethinking of how European countries plan for extreme heat. It prompted new public health protocols, new urban design guidelines, new ways of thinking about what the climate of the future might look like. And at the root of all of it was a jet stream that had shifted northward. That had, for reasons still being studied, locked into an unusual pattern and stayed there, a river of air 7 miles above the ground that decided for a few weeks to take a different path, and in doing so, killed tens of thousands of people. Here is something that most people do not know, and I think it is worth knowing: the jet stream does not just affect the mid-latitudes. Its influence reaches into the tropics in ways that are only now being fully appreciated. When the jet stream dips unusually far south, it can interact with tropical moisture and help generate or intensify weather systems far from its typical position. When it stalls, when the Rossby waves slow down and the usual west to east progression of weather systems grinds to a halt, the result is what meteorologists call a blocking pattern. High-pressure blocks can park themselves over a region for weeks, producing either prolonged heat and drought or, on the cold side of the block, prolonged cold and flooding rain. The Russian heat wave and Pakistan flooding of 2010 occurred simultaneously because of exactly this kind of blocking pattern, a stalled wave in the jet stream that locked warm, dry air over Russia and funneled extraordinary moisture into Pakistan at the same time. Record heat in one place, record floods thousands of miles away, caused by the same kink in the same river of air. Have you ever noticed that some rainy seasons seem to drag on for weeks without a break, while other times a sunny stretch seems to last forever? That is often blocking at work. The jet stream stuck in a loop, delivering the same kind of weather day after day, with none of the usual variability that comes from weather systems, tracking steadily eastward beneath it. Now, I mentioned at the very beginning of this section, the trade winds, those persistent easterly surface winds in the tropics that powered 5 centuries of human exploration and trade. Let me spend a moment with them, because their story is inseparable from the story of how the modern world was built. The trade winds blow from the northeast in the tropics of the northern hemisphere, and from the southeast in the tropics of the southern hemisphere, converging toward the equator in a band called the Intertropical Convergence Zone, or ITCZ. a region of rising air, intense convection, and heavy rainfall that migrates north and south with the seasons roughly following the sun. Sailors in the age of exploration learned to find the trade winds and use them as highways. The Spanish treasure fleet route from the Americas to Spain, the Manila galleons, the silver fleets from Peru and Mexico was entirely organized around the trade winds and the westerlies. Ships sailed west from Spain, on the trade winds crossed the Atlantic, loaded their silver and gold, then sailed north to catch the westerlies blowing back toward Europe. The route was not chosen for scenic reasons. It was chosen by the atmosphere. The Spanish Empire was in a very literal sense built on atmospheric physics, and the zone where the trade winds converge, the ITCZ, has its own haunting history. Sailors crossing the Atlantic who moved too close to the equator would sometimes find themselves becalmed in a region where the trade winds from the north and south met and canceled each other out, leaving the sea as flat and motionless as glass. With no wind, sailing ships could not move. They could be stuck for days or weeks. Fresh water ran short, food spoiled in the heat. Animals carried as cargo horses' cattle would sometimes die of thirst and have to be thrown overboard. This region, for this reason, came to be known as the horse latitudes, though the exact origin of that name is debated by historians. It was a place where the wind's absence was as consequential as the wind's presence, a reminder that the map of the wind has zones of stillness as well as corridors of power. Here is the common misconception I want to address directly, because it comes up often when people discuss winds and weather, the idea that wind patterns are variable and shifting, that they blow randomly in different directions from year to year, that they cannot be predicted or relied upon. This is wrong in a fundamental way. The large-scale wind belts of Earth, the trade winds, the westerlies, the polar easterlies, the jet streams, are remarkably stable in their broad character. They shift seasonally, they vary in intensity from year to year, they can be displaced temporarily by blocking patterns or ENSO events. But the basic structure, the fact that the trade winds blow from the northeast in the northern hemisphere, tropics that the westerlies blow from the southwest, in the mid-latitudes that the polar jet streams meander between roughly 30 and 70 degrees latitude. This structure is as reliable as the rotation of the Earth itself, because it is caused by the rotation of the Earth itself. The Coriolis effect that deflects moving air, the circulation cells that organize that deflection into belts, these are not temporary features. They are expressions of fundamental physics operating on a spinning sphere in the light of a distant star. The wind has a map. It has always had a map. And for most of human history, the people who understood that map best, who had memorized its seasonal variations, who knew how to read its shifts from cloud patterns and wave behavior, and the behavior of birds, those people had an advantage that translated directly into survival, into trade, into the building of civilizations across oceans. The Polynesian navigators who settled the Pacific, one of the greatest feats of exploration in human history, accomplished without instruments, without written maps, without any of the tools European sailors considered essential, did so in large part by reading the wind. They knew which winds blew in which season, at which latitude. They knew how the trade winds changed at the edges of the ITCZ. They read the swell patterns of the ocean, which are themselves generated by distant winds, to infer the position of islands beyond the horizon. Their knowledge of atmospheric and oceanic patterns was not written down. It was carried in memory, passed from navigator to navigator, across generations, a living library of planetary physics encoded in the minds of human beings. That knowledge, that intimate embodied generational knowledge of the wind's map, was for millennia one of the most valuable things a human being could possess. And yet, for all the patterns the wind follows, for all the reliability of the jet streams and the trade winds and the great circulation cells, there is a quality to the atmosphere that resists the very idea of a map. A sensitivity so extreme, a dependence on initial conditions so profound that even with perfect knowledge of the wind's structure, perfect prediction remains forever just out of reach. Not because the atmosphere is random, but because it is alive in a way that mathematics is still learning to describe. And the man who first understood this, who first glimpsed the true depth of the atmosphere's complexity, found it not in the sky, but in a number with 6 decimal places that he decided one afternoon in 1961 to round to 3. In December of 1972, a meteorologist named Edward Lorenz delivered a talk at the annual meeting of the American Association for the Advancement of Science. The title of his talk was a question posed with a quiet playfulness that masked the depth of what lay beneath it. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? He did not answer the question with a simple yes or no. He was too careful a scientist for that. But the image lodged itself in the public imagination so completely, so irrevocably, that 50 years later, it remains one of the most recognized metaphors in all of science, a shorthand for the idea that small causes can have enormous consequences, that the world is more sensitive to its initial conditions than we ever imagined, and that the future even of something as concrete and physical as the weather above our heads may be fundamentally, irreducibly uncertain. But here is what almost nobody knows about that butterfly. The story behind it is not a thought experiment. It is not a metaphor that Lorenz invented at a desk. It is a discovery that happened by accident on an ordinary afternoon in a small office at MIT, when a man made a decision that seemed completely insignificant and changed our understanding of nature forever. The year was 1961. Edward Lorenz was running a weather simulation on one of the early electronic computers of the era, a Royal McBee LG P30A machine, roughly the size of a refrigerator, that could perform perhaps 60 mathematical operations per second. By modern standards, it was almost unimaginably slow. But for Lorenz, it was a window into the atmosphere's behavior, a way of running simplified mathematical models of the weather, and watching how they evolved over time. On that particular afternoon, Lorenz wanted to re-examine a sequence of results his simulation had already produced. To save time, instead of restarting the simulation from the very beginning, he entered the values from the middle of the previous run, the state of the atmosphere at a specific point in the simulation, and let it run forward from there. He went for a cup of coffee. He expected to come back and find results essentially identical to what the simulation had produced before. After all, he was starting from the same point. The physics was the same, the equations were the same. The only difference was a tiny one, an irrelevant one or so. He thought. The computer stored numbers to 6 decimal places internally, but when it printed them out, it rounded to 3. Lorenz had entered the printed 3 decimal values. The difference between what the computer remembered and what Lorenz typed in was something like 0.0000127, less than 1/10,000th. When he came back from his coffee, the simulation had diverged completely from the original, not slightly, not in small ways that accumulated gradually, dramatically, fundamentally beyond recognition. The 2 runs started from what appeared to be the same point and had evolved into completely different weather patterns. A difference of 1 part in 10,000 in the initial conditions had, within the time frame of the simulation, produced entirely different outcomes. Lorenz stared at those results for a long time, and then, being the kind of scientist he was, careful, rigorous, not given to hasty conclusions, he checked everything. He verified the equations. He checked for computer errors. He ran the simulation again. The result was the same. The divergence was real. It was not a bug. It was a feature of the equations themselves, a feature he slowly realized of the atmosphere they were modeling. What Lorenz had discovered and would spend the next decade formalizing into a rigorous mathematical theory was what we now call sensitive dependence on initial conditions. The idea that certain systems in the atmosphere, as one of them, are so exquisitely sensitive to their starting state that even unmeasurably small differences in the initial conditions lead over time to completely different outcomes. Not because the system is random. The equations Lorenz was using were entirely deterministic. Every output followed mathematically and inevitably from the input. but the sensitivity was so extreme that in practice for any real physical system, you could never measure the initial conditions precisely enough to predict the long-term outcome. You could always be wrong in the 10,000th decimal place, and in a chaotic system, being wrong in the 10,000th decimal place eventually means being wrong about everything. This was the genuinely revolutionary idea, and it had a direct, profound, and at the time deeply uncomfortable implication for meteorology. There is a fundamental physical limit to how far in advance weather can be predicted. Not a technological limit, not something that better computers or more observations could overcome. A mathematical limit built into the nature of the atmosphere itself. Lorenz estimated that limit at roughly 2 weeks. Beyond about 14 days, the atmosphere's sensitivity to initial conditions, the inevitable tiny errors in any measurement of the current state of the atmosphere, would have amplified to the point where a forecast contains essentially no useful information. The atmosphere would have forgotten in a mathematical sense where it started. 2 weeks. After centuries of observation, after satellites and radar and radio sondes and supercomputers, 2 weeks is roughly where the wall stands. Not because we are not trying hard enough, not because the models are not good enough, because the mathematics of the atmosphere itself will not permit it. Now, I want to address the butterfly question directly, because the popular understanding of it contains a significant and important misconception, one that I think actually makes the real story less interesting than it is not more. The popular version of the butterfly effect is often interpreted to mean, yes, literally, a butterfly flapping its wings in Brazil can cause a tornado in Texas. That small actions have enormous traceable consequences. That if you could just prevent that butterfly from flapping, you could prevent the tornado. This interpretation is in an important sense wrong, or at least deeply misleading. Here's the more careful version. In a chaotic system like the atmosphere, tiny perturbations of which a butterfly's wing flap is a poetic example do not cause specific outcomes. They do not create specific tornadoes. What they do is alter infinitesimally at first, and then increasingly dramatically over time, the trajectory of the entire system. The butterfly does not cause the Texas tornado. What the butterfly does, or more precisely, what the class of infinitesimal perturbations that a butterfly represents, is make it impossible in principle to predict whether a tornado will form in Texas 2 weeks from now. Because any model of the atmosphere that does not include the butterfly's wing flap, and no model can include every butterfly in Brazil, is already from the very first moment slightly wrong, and that slight wrongness grows, and grows, until the forecast is meaningless. The butterfly effect is not a statement about causation. It is a statement about predictability. It is not saying that small things cause big things. It is saying that in certain systems, the precision required to predict the future grows without bound as you look further forward in time. And the atmosphere is one of those systems. Lorenz published his key findings in a 1963 paper titled Deterministic Non-Periodic Flow, one of the most cited papers in the history of the atmospheric sciences, and one of the founding documents of what would become chaos theory. In that paper, he described a simplified set of equations representing atmospheric convection, and showed that their solutions never repeated exactly, never settled into a regular pattern, and were exquisitely sensitive to initial conditions. He visualized the behavior of his equations as a trajectory in a mathematical space, a trajectory that traced out a shape now known as the Lorenz attractor. It looks in 3 dimensions, something like 2 intertwined spirals, or the wings of a butterfly, which is perhaps why the metaphor found such a natural home in this particular piece of science. The shape the equations traced was not random. It had structure order, a characteristic form, but it never repeated. It was ordered chaos, pattern without predictability, structure without repetition. This is the deep truth about weather that chaos theory revealed. The atmosphere is not random, and it is not predictable. It is something in between, something that has patterns and tendencies and structures, but that is too sensitive to its own initial conditions to be traced far into the future. This is not a failure of science. It is a discovery about nature, a discovery that the universe contains systems that are deterministic, that follow physical laws exactly without exception, but that are nonetheless in practice unpredictable beyond a certain horizon. Have you ever wondered why a 10-day forecast is so much less reliable than a 3-day forecast? Not a little less reliable, dramatically less reliable. This is why. Each day of forecast horizon, the small errors in the initial conditions have more time to grow. By day 3, forecast skill is still quite good. By day 7, it is degraded noticeably. By day 10, it is catching broad patterns but missing the details. By day 14, it is in statistical terms not much better than climatological averages. The atmosphere has, mathematically speaking, forgotten where it was 2 weeks ago. Modern meteorology has developed a beautiful and ingenious response to this fundamental limitation called ensemble forecasting. Instead of running a single weather model from a single best estimate of the current atmospheric state, which will inevitably be wrong in the 10,000th decimal place in some measurements, ensemble forecasting runs dozens or hundreds of model simulations simultaneously, each starting from a slightly different version of the initial conditions, each perturbation calibrated to represent the measurement uncertainty in the observational data. The ensemble of forecasts spreads out over time as the simulations diverge, and the spread itself becomes information. Where the ensemble members agree, forecasters have high confidence. Where they diverge, forecasters know the atmosphere is in a sensitive state, that multiple outcomes are genuinely possible, and that uncertainty should be communicated honestly to the public. This is a profound philosophical shift from the way weather forecasting was once conceived. The old dream, dating back to the early days of numerical weather prediction in the 1950s, was to build a model good enough to produce a single definitive forecast, a perfect prediction. Chaos theory and the work that flowed from Lorenz's discovery showed that dream to be not just difficult, but physically impossible beyond a certain horizon. The new goal is not certainty. The new goal is honest, calibrated uncertainty. Not "it will rain on Thursday," but "there is a 70% probability of rain on Thursday," with the uncertainty arising from these specific features of the current atmospheric state. Probability not as a confession of ignorance, but as a precise scientific statement about a system that is genuinely mathematically uncertain. There is a lesson here that extends well beyond meteorology, and I think it is one of the quietest and most important lessons that weather science offers to anyone willing to sit with it. We live in a culture that is deeply uncomfortable with uncertainty. We want definitive answers. We want to know with confidence what will happen. And when forecasters say there is a 40% chance of rain, many people hear that as a hedge, a failure, a sign that the meteorologists don't really know. But 40% is not ignorance. 40% is a precise and honest statement about a physical system that has been studied with extraordinary care by thousands of scientists using the most powerful computers on Earth. And that still, because of the mathematics of chaos, because of the butterfly and its wings, cannot be pinned down to certainty. The uncertainty is real. It is quantified. It is science at its most honest. Edward Lorenz himself was by all accounts a quiet and modest man. He did not seek fame. He did not dramatize his discoveries. He continued working at MIT into his 80s, publishing careful, rigorous papers, attending conferences, mentoring students. When asked about the butterfly effect and its popularization, he was characteristically careful in his language, pleased that the idea had reached a wide audience, but precise about what it actually meant. He died in 2008 at the age of 90, having given the world one of its most important scientific insights: the understanding that nature contains systems which follow rules exactly, but whose futures are nonetheless beyond our reach. The atmosphere follows rules. Every molecule of air obeys the laws of physics without exception, without deviation, without randomness. And yet the weather 2 weeks from now is genuinely unknown, not because we are ignorant, but because the system itself, given its sensitivity, will not hold still long enough to be predicted, ordered, chaotic, both at once. And if the atmosphere's natural complexity already makes long-range prediction so profoundly difficult, imagine what happens when you begin to change the atmosphere itself, when the composition of the air changes, when the ocean warms, when the ice melts, when the energy budget of the entire planetary system shifts in ways that have no precedent in the 10,000-year span of human civilization. The chaos does not go away. It does not simplify. If anything, it deepens. But the patterns beneath the chaos, the tendencies, the fingerprints of a changed climate pressing through the noise of daily weather, those patterns are becoming clearer and more urgent with every passing year. There is a place in Antarctica at a research station called Vostok, where the ice beneath your feet is not simply frozen water. It is an archive, a library written in bubbles, tiny pockets of ancient air, trapped in snow that fell hundreds of thousands of years ago, and was slowly compressed over millennia into ice. Each bubble is a sealed sample of the atmosphere as it existed at the moment that snowflake landed. The temperature at the time of snowfall is encoded in the ratio of oxygen isotopes in the ice itself. Layer by layer going deeper means going further back in time, the way the rings of a tree record each passing year. But on a scale so vast, it makes the mind go quiet. In 1998, after decades of drilling through nearly 2.5 miles of Antarctic ice, the Vostok Ice Core project reached ice that had formed approximately 420,000 years ago. What the scientists found in those ancient bubbles was, in the truest sense of the word, staggering. They had recovered a continuous record of atmospheric composition and temperature spanning 4 complete ice age cycles, 4 great oscillations between cold glacial periods and warm interglacial periods, each cycle lasting roughly 100,000 years. And what that record showed with a clarity that left no room for interpretation was a relationship so tight, so consistent, so perfectly repeated across 420,000 years that it looked almost like a law of nature. When carbon dioxide in the atmosphere went up, temperature went up. When CO2 went down, temperature went down. The two curves tracked each other through 4 complete ice ages with a fidelity that was beautiful, and once you understood what it meant for the present, deeply sobering. The CO2 levels in those ancient ice cores never exceeded about 300 parts per million during any of the 4 warm interglacial periods, the warmest, most hospitable phases of Earth's recent climate history. Never in 420,000 years of atmospheric record. The level when the Vostok core was published in 1998 was approximately 365 parts per million. Today, as of the most recent measurements, it exceeds 420 parts per million, higher than at any point in at least 800,000 years of ice core record and almost certainly higher than at any point in the last 3 million years. We have changed the atmosphere. Not metaphorically, not as a policy position or a political claim. Chemically, measurably, verifiably, we have changed the composition of the air that surrounds this planet, and we have done it in the span of roughly 150 years. In geological terms, that is not even a blink. It is something closer to a single heartbeat in the long, slow life of the Earth. And the atmosphere, which we have been learning to listen to throughout this entire journey tonight, is responding. But before we go any further, I want to address something directly, because one of the most persistent and consequential confusions in public discussions of climate is the confusion between weather and climate. And getting this distinction right is not just scientifically important. It is the foundation upon which everything else in this section rests. Weather is what happens in the atmosphere over hours, days, and weeks. It is the rain falling outside your window tonight. It is the temperature on Tuesday, the storm system moving through on Thursday, the unexpected warm spell in February. Weather is specific local short-term. It is governed by the chaos we explored in the last section. Sensitive variable, ultimately unpredictable beyond about 2 weeks. Climate, by contrast, is the pattern, the average. the statistical behavior of the atmosphere over decades and centuries. Climate is not what the weather is doing right now. Climate is what the weather tends to do over long periods in a given region. The confusion between these two things, weather and climate, produces one of the most common and most misleading arguments in public discourse about the changing atmosphere. You have almost certainly heard some version of it. It snowed last week, so how can the planet be warming? The answer is that a snowstorm in January is weather. It tells you something about the state of the atmosphere on that particular day in that particular place. It tells you nothing about the 30-year trend in global average surface temperatures. These are measurements at completely different scales, and comparing them is like pointing to a single wave as evidence about the direction of the tide. The wave and the tide are both real. The wave does not disprove the tide. Climate scientists understand this distinction better than almost anyone, and they are careful in their work to communicate it. But the confusion persists in public discourse, partly because weather is immediate and visceral and personal. You can step outside and feel it, while climate is statistical and abstract and slow. The human mind is not naturally calibrated for 30-year trends. It is calibrated for the immediate. And that calibration mismatch is one of the deepest challenges in communicating climate science to a general audience. Now, let me tell you about feedback loops because they are, I think, the most important and least understood concept in all of climate science. And once you understand them, the way you think about a warming planet will never quite be the same. A feedback loop in any system is a process where the output of a system feeds back into the system as input amplifying or dampening the original change. In the climate system, there are both positive feedbacks, which amplify warming, and negative feedbacks, which dampen it. The balance between them determines how sensitive the climate is to changes in greenhouse gases, and the feedbacks are numerous, interconnected, and operating at every scale from the microscopic to the planetary. The ice albedo feedback is perhaps the most visually intuitive. Ice and snow are bright. They reflect roughly 80 to 90% of incoming solar radiation back into space. Dark ocean water and bare soil reflect only about 6 to 10%. They absorb the rest as heat. When ice melts, it exposes dark ocean or soil beneath it. That darker surface absorbs more heat. The additional heat melts more ice, which exposes more dark surface, which absorbs more heat. The original warming is amplified by its own consequences. This is a positive feedback, not positive in the sense of good, but positive in the mathematical sense of self-amplifying. And it is already operating measurably in the Arctic, where sea ice extent has declined dramatically over the past 4 decades, and where temperatures are rising roughly 4 times faster than the global average. The Arctic is warming faster than anywhere else on Earth, partly because of the ice albedo feedback accelerating the process that began it. The water vapor feedback is even more powerful, though less visually obvious. Water vapor is itself a greenhouse gas. In fact, it is the most abundant greenhouse gas in the atmosphere, responsible for more of the natural greenhouse effect than CO2 alone. But water vapor in the atmosphere is controlled by temperature. Warmer air holds more water vapor. So, when CO2 warming raises the temperature, more water evaporates into the atmosphere. More water vapor traps more heat. The temperature rises a little more water evaporates. Scientists suggest that the water vapor feedback roughly doubles the warming that would result from CO2 alone. CO2 is the dial that gets turned. Water vapor is the amplifier that makes the effect far larger than the original perturbation. The permafrost feedback is slower, but potentially enormous in its consequences. Permafrost permanently frozen ground across vast areas of Siberia. Canada and Alaska contains enormous quantities of organic carbon, the remains of plants and animals that died and were frozen before they could fully decompose, accumulating over tens of thousands of years. Researchers estimate that the world's permafrost contains roughly 1.5 trillion tons of carbon, about twice as much carbon as is currently in the entire atmosphere. As permafrost thaws, that organic material begins to decompose. Decomposition releases CO2, and methane, both greenhouse gases, with methane being roughly 80 times more potent than CO2 over a 20-year time frame. Warming thaws the permafrost. Thawed permafrost releases greenhouse gases. Greenhouse gases warm the climate, which thaws more permafrost. This is another positive feedback operating on a time scale of decades to centuries, with a potential scale of impact that is genuinely difficult to fully model. I want to pause here for a moment, because I think it is important to say something clearly describing positive feedbacks and their potential consequences is not the same as predicting doom. Science is not in the business of predicting doom. It is in the business of understanding processes and communicating what those processes imply as honestly and as carefully as possible. The permafrost feedback is real and potentially significant. It is also something that can be studied, monitored, modeled, and in principle, if emissions are reduced, sufficiently partially mitigated. Understanding the feedback is the first step toward any meaningful response to it. Now, let me bring in a piece of history that I find both fascinating and deeply instructive, the story of how scientists first understood that human activities could change the climate. Because this understanding did not arrive suddenly, it was built piece by careful piece over more than a century by a series of scientists whose contributions were often overlooked or dismissed in their time. In 1856, an American scientist named Eunice Newton Foote conducted an experiment so simple that it could be performed in a kitchen and so profound that it would eventually reshape our understanding of the planet. She filled glass cylinders with different gases, air, carbon dioxide, water, vapor, and placed thermometers inside them. She set them in sunlight. She measured how much each gas heated up. Her result was clear. The cylinder filled with carbon dioxide heated more than the others and took longer to cool. In her published paper, she wrote with a prescience that is almost breathtaking in retrospect, that if the Earth's atmosphere had a higher proportion of carbonic acid, the temperature would be elevated. She was right, and she was almost entirely ignored. Her paper was presented at the American Association for the Advancement of Science in 1856 by a male colleague because women were not permitted to present their own work. Her finding was not cited, not followed up, not incorporated into the scientific literature in any significant way. 3 years later, the Irish physicist John Tyndall conducted similar experiments on a larger scale and with greater precision, and is generally credited in most historical accounts as the discoverer of the greenhouse effect. Foote's work was largely forgotten, for over a century rediscovered only in 2011 when her original paper was found in the archives. Tyndall's work was followed in 1896 by the Swedish chemist Svante Arrhenius, who performed the first quantitative calculation of how much the Earth's temperature would change if the concentration of atmospheric CO2 were doubled. His answer, arrived at through months of painstaking hand calculation, was approximately 5 to 6 degrees Celsius of global warming for a doubling of CO2. Modern climate models using supercomputers and vastly more sophisticated physics give an estimate of roughly 5 to 4 degrees Celsius for a doubling of CO2. Arrhenius, working alone with pencil and paper in 1896, was in the right ballpark. He was not alarmed by his finding. He thought warming would be beneficial for Scandinavia, and imagined the process would take thousands of years. He did not foresee the rate at which industrial emissions would accumulate, but the physics was right. The mechanism was right. The direction was right. The question I find myself returning to, thinking about Foote and Tyndall and Arrhenius, about experiments conducted in the 1850s and 1890s that described with essential accuracy the process that is now reshaping the climate of the 21st century, is this: what does it mean to know something? What does it mean to have the knowledge, to have published the knowledge, to have the knowledge sitting in the scientific record for a century and a half, and still to have the consequences of that knowledge unfold as though it had never been known? This is not a question with a simple answer, but it is, I think, one of the most important questions that the history of climate science poses to us. Knowledge and action are not the same thing. Understanding a system and responding to what that understanding implies are separated by something political, something economic, something deeply human that science alone cannot bridge. The atmosphere does not negotiate. It does not wait for consensus. It responds to the composition of the gases within it according to the same physics that Foote measured in her kitchen in 1856, that Tyndall measured in his laboratory in 1859, that Arrhenius calculated at his desk in 1896. The greenhouse effect is not a theory in the colloquial sense of something uncertain or contested. It is a physical mechanism as well established as gravity, as well understood as the pressure of the atmosphere that Torricelli measured in 1643. The warming is happening. The fingerprints are in the ice cores, in the ocean heat content, in the retreat of glaciers on every continent, in the shift of seasons and the movement of species, poleward and upward in altitude, in the lengthening of fire seasons, in the intensification of rainfall extremes, as a warmer atmosphere holds more moisture and releases it more violently. Here is the critical point I want to leave clearly in the air before we move toward the closing of our journey. Tonight, the weather is not random as we have been learning all along. It follows rules. And those rules are not changing. What is changing is the environment within which those rules operate. The jet streams still flow. The pressure systems still rise and fall. The Coriolis effect still deflects moving air to the right in the northern hemisphere. The ocean still stores heat and breathes it back into the sky. Clouds still form when air rises and cools. The butterfly effect still limits forecasts to roughly 2 weeks. All of that, the deep physics of the atmosphere, is unchanged. What has changed is the energy level of the system. The amount of heat trapped, the temperature of the ocean surface, the extent of the Arctic ice, and a more energetic system operating under the same rules produces more extreme expressions of those rules, more intense rainfall, more severe droughts, more powerful storms drawing energy from warmer seas, longer heat waves sustained by a more persistent jet stream. The same music played louder, and that music, that ancient, intricate, rule-governed music of the atmosphere that we have been learning to hear throughout this entire night, is reaching a moment that has no precedent in human history. A moment where the patterns we built our civilizations around are shifting season by season, year by year, in ways that the ice cores and the sediment records and the careful observations of generations of scientists are only now allowing us to fully see. We changed the weather, quietly, incrementally, without fully understanding what we were doing across a century and a half of industrial activity. And now, with every measurement, every ice core, every satellite pass, every careful reading of the atmosphere's ancient archive, the weather is telling us in the only language it has ever spoken exactly what we did. And what if we are willing to listen as carefully as those ancient Babylonian astronomers listened to the sky over Mesopotamia 4,000 years ago? We might still choose to do about it. There is one more thing to say, one more thread to gather. Because we have traveled tonight from the uneven warmth of the sun to the weight of the air, from the memory of the ocean to the language of the clouds, from the map of the winds to the mathematics of chaos, from the fingerprints of a changed atmosphere to the ancient ice that remembers what the air once was. And all of these things, every single one, have been pointing toward a single, quiet, profound idea that has been waiting at the end of this journey all along. There is a raindrop falling outside somewhere in the world right now. Maybe it is falling on a rice paddy in Vietnam, on a rooftop in Chicago, on the surface of the Amazon River, on the windshield of a car parked on a quiet street in a town whose name you have never heard. That raindrop did not appear from nowhere. It began as liquid water on the surface of some ocean somewhere between a few days and a few weeks ago. The sun warmed that ocean surface. The water evaporated, rising invisibly into the air as vapor. The wind carried it, perhaps thousands of miles, perhaps, across an entire ocean. Riding the trade winds or the westerlies or the circulation patterns of a passing storm system, it rose in a column of warm air, cooled at altitude, condensed around a particle of dust or sea salt or pollen, joined millions of other droplets to form a cloud. The cloud drifted steered by the jet stream. Pressure patterns organized the moisture. Temperature gradients determined when and where the cloud would release what it was holding. And then, obeying every physical law we have explored tonight, every rule of thermodynamics and fluid dynamics and Coriolis geometry and atmospheric chemistry, that raindrop fell. Not randomly, never randomly, according to a logic as old as the ocean itself. We have traveled a long way tonight, and I want to spend this final hour, this last quiet stretch, before you drift into sleep, gathering everything we have learned into something that feels not like a summary, not like a test, but like a recognition. The slow recognition of something you already knew somewhere beneath the surface, but had never quite been given the words to say. Let us go back to the beginning, not the beginning of this video, further back. Back to the moment when the first human being looked up at the sky before a storm and felt in their chest the wordless knowledge that something was coming. That person did not know about atmospheric pressure. They had never heard of the Coriolis effect. They did not know that the darkness of the clouds above them was caused by ice crystals and liquid water droplets in concentrations dense enough to block the passage of sunlight. They did not know that the electricity they felt in the air was the result of charge separation in a cumulonimbus column, or that the wind picking up around them was surface air rushing in to replace the warm air rising at the center of a developing low-pressure system. They knew none of this, and yet they knew. They felt the sky changing, and they responded. Because the body trained by millions of years of evolution in an atmosphere exactly like this one is itself an instrument, a rough one, an imprecise one, but a real one. What science has done, what 3,000 years of watching, recording, theorizing, measuring, calculating, and modeling has done, is not replace that instinct. It has explained it. It has given language to something that was always real, always physical, always rule-governed, but that for most of human history could only be felt, not understood. The Babylonians felt the ring around the moon and knew rain was coming. We now know they were detecting cirrostratus ice crystals in the advance of a warm front. Aristotle felt that weather must have natural causes and insisted on looking for them. Torricelli felt the weight of the sky and invented an instrument to measure it. Luke Howard looked up at clouds his entire life, and one afternoon gave them names that the whole world adopted within a decade. George Hadley sat with the mystery of the trade winds and traced them back to the uneven heating of a sphere. Wilhelm Bjerknes brought the mathematics of physics to the atmosphere and showed that storms were not chaos, but process. Edward Lorenz rounded a number to 3 decimal places and discovered that the future was more mysterious than anyone had imagined. Eunice Newton Foote set glass cylinders in the sunlight and measured with kitchen experiment simplicity the force that would reshape the 21st century. Each of these people was doing the same thing in their own time with their own tools. They were listening, carefully, patiently, rigorously. They were learning the language of the sky. And here is what all of them discovered, each in their own way. The weather is not random. It is not the whim of gods or the breath of spirits or the unpredictable tantrum of a chaotic universe. It is the expression of physical laws operating continuously at every scale, from the molecular to the planetary, across time spans. From the fraction of a second it takes for a water droplet to form around a dust particle to the 100,000-year cycles of ice ages recorded in the ancient layers of Antarctic ice. It is ordered. It is lawful. It is in the deepest sense knowable, not completely, not infinitely far into the future, not down to the last raindrop on the last rooftop, but knowable in its patterns, its tendencies, its grand architecture of cause and effect. And yet, and this is the thing I most want you to carry with you into sleep tonight, knowing that the weather follows rules does not make it less wondrous. If anything, it makes it more so. Consider what it means that the rain falling right now on that rice paddy or that rooftop began its journey as evaporation from an ocean traveled thousands of miles, on winds driven by the uneven heating of a tilted planet by a star 93 million miles away, was organized into clouds by pressure differences caused by the weight of 5 quadrillion tons of air pressing down on the Earth's surface, was steered by a jet stream created by the Coriolis effect of a spinning planet, and fell at precisely this moment in precisely this place, because of a chain of physical causes stretching back further than any individual storm, any individual season, any individual century. The rain is not random. The rain is the universe following its own rules all the way down at every step, without exception. And those rules, it turns out, are beautiful. Here is a question worth carrying into the quiet of tonight. Have you ever stood in the rain and just let it fall on you? Not rushed for cover, not cursed the weather, app that got it wrong, not pulled up your hood and hunched your shoulders against it, but just stood there feeling it land one drop at a time. Each of those drops completed a journey measured in thousands of miles and dozens of days, driven by the same physics that governs the formation of galaxies and the motion of planets, the same conservation of energy, the same fluid dynamics, the same thermodynamics. You standing in the rain are standing at the end of a chain of physical causes that reaches back to the birth of the ocean, to the first time sunlight touched liquid water on this young planet, to the very beginning of the atmosphere itself. The weather is not happening to you. You are part of it. You are standing inside one of the universe's most intricate, most beautiful, most ancient physical systems, and it is raining. Now, I want to tell you something about the future of weather science that I find quietly thrilling, because this story is not finished, not even close. In 2023, a team of researchers at Google DeepMind released a weather forecasting system called GraphCast, an artificial intelligence model trained on 4 decades of historical weather data. In independent tests, GraphCast outperformed the best traditional numerical weather prediction models on roughly 90% of forecast variables, producing 10-day forecasts in under a minute on a single computer. A single computer. The kind of forecast that previously required a supercomputer running for hours. The implications are extraordinary, not just for the speed and accessibility of weather forecasting, but for what it reveals about the structure of weather itself. The AI learned to forecast weather not by being given the equations of atmospheric physics, but by finding the patterns in the data, by learning from 40 years of observations what the atmosphere tends to do. In a sense, GraphCast is doing something not entirely unlike what the ancient Babylonians did, finding patterns in the sky's behavior, but at a scale and precision that is simply incomparable. Does this mean we have solved weather forecasting? No. The 2-week wall that Lorenz identified has not moved. The chaos is still there, still fundamental, still mathematical. GraphCast cannot predict the weather 3 weeks from now any better than traditional models can. The butterfly effect has not been repealed. But within the predictable window, the 2 weeks where the atmosphere still remembers where it started, the tools are becoming extraordinary. And the application of machine learning to climate modeling, to long-range pattern prediction, to the understanding of how a warming planet will shift the statistics of extreme weather events, these are areas of rapid, exciting, genuinely transformative progress. We are right now living through one of the most remarkable periods in the history of atmospheric science. We have instruments that can measure temperature and pressure and humidity and wind speed at millions of points simultaneously, from satellites in orbit and balloons in the stratosphere and buoys in the ocean and weather stations on every continent, including Antarctica. We have models that simulate the global atmosphere at resolutions of a few kilometers, updated every hour, running on computers, performing quintillions of operations per second. We have ice cores that give us 800,000 years of atmospheric history. We have sediment records that extend millions of years further back. We have the mathematical framework of chaos theory to tell us what we cannot predict, and the growing power of machine learning to push the boundaries of what we can. We have more knowledge of the atmosphere than at any point in the entire history of our species. And still on a night like tonight, lying quietly listening to the rain or the wind or the silence, the sky retains its mystery. The specific raindrop on the specific rooftop is still beyond prediction. The exact moment when the storm will pass and the stars will reappear is still uncertain. The chaotic, sensitive, beautiful, rule-governed atmosphere is still larger than our ability to fully contain it in any model or any equation or any satellite image. There is, I think, something right about that. Something fitting. The universe should be slightly larger than our understanding of it. That gap between what we know and what remains to be known is not a failure. It is an invitation. It is what keeps the scientists watching the instruments measuring the models running. It is what keeps the rest of us looking up. I want to end tonight with one final image. Not a scientific finding, not a historical fact, but a picture the kind that I hope carries something into sleep with you. Somewhere in the upper atmosphere right now, at roughly 35,000 feet above the surface of the Earth, the polar jet stream is flowing. It is moving at perhaps 150 miles per hour eastward in a great sweeping curve across the northern hemisphere, sometimes dipping south toward the tropics, sometimes looping north toward the pole, its path shaped by the mountains below it. And the temperature contrasts on either side of it, and the season and the state of the Arctic ice, and 100 other factors that feed back into each other in the endlessly complex way that Lorenz glimpsed in 1961. It has been flowing in some form for millions of years. It flowed above the dinosaurs. It flowed above the first human beings who ever looked up at the sky. It flowed above the Babylonians, writing their cloud observations on clay tablets above Luke Howard, watching from London, above Lorenz, drinking his coffee while his computer diverged above all of it, above all of us, steady and vast and following its rules exactly without exception, without pause, without rest. Below it at the surface, the weather happens. Storms form and dissolve. Rain falls and evaporates. Snow accumulates and melts. Heat waves build and break. Fog forms in valleys at dawn and burns off by mid-morning. The barometer rises and falls. The clouds move through their sequence cirrus to cirrostratus to altostratus to nimbostratus, writing the arrival of weather in a language that Luke Howard gave us the vocabulary to read. The ocean breathes its moisture into the air, and the air carries it thousands of miles, and the mountains force it upward, and the upward motion cools it, and the cooling condenses it, and the condensed water falls as rain, or snow, or sleet, or hail, returning eventually to the ocean, or the river, or the groundwater, waiting to evaporate again, to begin the journey, again to fall again, somewhere new. It is a cycle. It has always been a cycle. Water and air and heat and pressure and spin going around and around in a loop that began when the first oceans formed on this young planet roughly 4 billion years ago, and that will continue long after the last human being has looked up at the last cloud in the last afternoon sky. The weather is older than life. It shaped the conditions in which life arose. It fed the first photosynthesizing organisms that filled the atmosphere with oxygen. It carved the canyons and deposited the river deltas and shaped the coastlines where the first cities were built. It carried the spores and the pollen and the dust that carried life from continent to continent. It is not background. It is not scenery. It is the medium in which life on Earth has always lived, as much a part of our world as the ground beneath our feet or the sun above our heads. And it was never random. It was always speaking, always following its rules, always writing its messages in clouds and pressure and wind in the ring around the moon, and the stillness before a storm, and the particular color the sky turns just before the rain. We just needed all along to learn how to listen. I hope that on the next rainy day, or the next clear one, or the next morning, when you step outside and feel in the quality of the air, something changing, you hear a little more of what the sky is saying. I hope you feel the weight of the atmosphere pressing gently down on your shoulders and know that you are feeling 5 quadrillion tons of air that has been in motion since before your species existed. I hope you look up at the clouds and see in their shapes and their heights and their sequences the language that Luke Howard spent his evenings learning to read. I hope you feel the wind and know it is the atmosphere's answer to a question. The sun asked, how do we balance what has been made unequal? I hope you feel in all of it the deep and ordered and beautiful complexity of a system that is not random, not chaotic in the way that word is usually meant, not mysterious in the way that things are mysterious when they have no explanation, but mysterious in the far better way. The way that things are mysterious when their explanation turns out to be more wonderful than the mystery itself. The weather is not random. It never was. It was just waiting for us to learn its language. And we are still learning. Quietly, patiently, one observation at a time, the way we have always learned the things that matter most. Thank you. Genuinely from somewhere quiet and grateful. Thank you for spending this night with the sky. For letting these ideas drift through you slowly, the way weather moves through a landscape, touching everything lightly and leaving something changed. If this journey brought you any peace, any wonder, any of that particular feeling of the world, becoming just slightly larger and more interesting than it was before, then it was worth every word. If you are still awake, and some of you are, I hope the next story finds you in the same quiet place, ready to drift into something new. There is so much left to explore. The universe does not run short of wonder, and neither do we. Sleep well, dream gently, and the next time it rains just for a moment, let yourself feel how far that water traveled to reach you. Good night,